In this section, we will focus on analyzing a suspension bridge and figuring out how the load is transferred. We will mainly look at the Golden Gate Bridge as an example. The main components of the bridge are the anchorages, towers, the deck, the main cables, and the suspenders. This is a quick diagram to explain how the components are working. As you can see, the cables and suspenders are undergoing tension. They are physically holding the deck and all the loads acting on the deck. The suspenders transfer the loads to the cables, and the cables transfer the loads to the towers. The towers, on the other hand, are undergoing compression. They are withstanding the loads of the bridge and transferring them to the ground. Let's work on this example together. The main span of a demonstration suspension bridge is to be 120 meters long. The deck is to be 10 meters wide, and the suspenders are to be spaced 8 meters apart along the length of the bridge. The deck will carry a live load of 15 kilopascals and a dead load of 10 kilopascals. The deck can be considered to consist of beams that run parallel to the bridge length and are 0.5 meters wide. These beams will rest on 12-meter-long cross beams that transfer their loads to the suspenders. The first non-horizontal segments of the main cables will have a slope of 4% to the horizontal. Here's a quick cross-section of one of the deck segments. As you can see, 0.5-meter wide deck beams run parallel to the bridge and are 8 meters long. Suspenders are 10 meters apart, and cross beams are 12 meters long. This is the mid-deck segment. The slope of the main cable following the horizontal segment is 4% radians. Let's work on the first question. The deck beams carry a UDL of. Now let's remember that the deck carries a live load of 15 kilopascals and a dead load of 10 kilopascals. Therefore, the UDL is the sum of those two loads, which is 25 kilopascals. The total load on the beam is each beam is carrying 25 kilopascals, with each beam having dimensions of 0.5 meter wide and 8 meter long. Therefore, each beam is carrying 100 kilonewtons. For purposes of calculating reactions, we can replace the UDL with a point load of magnitude 100 kilonewton at the center of the beam. Thus, the reactions that the crossbeam must provide at each end of the deck beam are: taking into consideration that the beam is symmetric and the load is applied at the center, the support reactions by the crossbeam on the deck beam should be equal on either sides of the beam. Let FA and FB represent the crossbeam reactions. Using the equations of equilibrium, we calculate FB to be 50 kilonewtons upward and FA to also be 50 kilonewtons upward. Therefore, the crossbeams must provide 50 kilonewtons per 0.5 meter of deck width at the end of each deck beam. The deck beams produce a load on the crossbeams of. Using the concept of action and reaction forces, since the crossbeam must provide 50 kilonewtons per 0.5 meter of deck width at the end of each deck beam, then the deck beam produces a load of 50 kilonewtons per 0.5 meters, which is equivalent to 100 kilonewtons per meter. Keep in mind that each crossbeam supports the two pairs of deck segments, 20 beams on one side and 20 beams on the other. We thus have another beam, this one with a UDL of 200 kilonewtons per meter. And now taking into consideration that the deck is only 10 meters wide, therefore the UDL is 2 meganewtons. Thus, the reactions that the suspender must provide at each end of the crossbeam are: taking into consideration that the crossbeam is symmetric and the beam load is applied at the center, the support reactions by the suspenders on the crossbeam should be equal on either sides of the beam. Let FC and FD represent the suspender reactions. Using the equations of equilibrium, we calculate FD to be 1 meganewton upward and FC to also be 1 meganewton upward. Therefore, the reactions that the suspenders must provide at each end of the crossbeam are 1 meganewton. Now moving on to analyzing the main cable. The deck is 120 meters long. Therefore, with each deck beam being 8 meters long, the bridge consists of 15 deck segments. As you can see below, if we were to examine one side of the bridge, we have 7 suspenders connected to the main cable. we will be studying points G, H, I, and M. Consider the point G where the first suspenders to the right of the bridge center connects to the main cable. We have 1 meganewton downward supporting the crossbeam, T0, which is the tension force to the left of that point, and T1, which is the tension force to the right of that point. It's given in the question that T1 is at an angle of 0.04 radians with the horizontal. Therefore, let's take the components into consideration. Using the equations of equilibrium at point G, we find that T1 is 25 meganewtons and T0 also about 25 meganewtons to the left. Therefore, the tension in the main cable at point G is 25 meganewtons. Consider the point H where the second suspender to the right of the bridge center connects to the main cable. So same thing as before, F1 and F2 are the suspender reactions supporting the crossbeam. T0 is the tension to the left of point G, and T2 is the tension to the right of point H. The angle at which T2 is projected is unknown, therefore we will be dealing with the components. Now using the equations of equilibrium, we find that T2y is 2 meganewtons and T2x to be around 25 meganewtons, which gives us T2 to be around 25.08 meganewtons. Using the components, the angle can be determined to be 0.08 radians. Now let's consider point I, where the third suspender to the right of the bridge center connects to the main cable. Similar to before, F1, F2, and F3 are the suspender reactions supporting the crossbeam, T0 is the tension to the left of point G, and T3 is the tension to the right of point I. The angle at which T3 is projected is unknown, therefore we will be dealing with the components. Now using the equations of equilibrium, we find that T3y is 3 meganewtons and T3x to be around 25 meganewtons, which gives us T3 to be 25.18 meganewtons. Using the components, the angle can be determined to be 0.12 radians. And now finally, let's consider the point M where the last suspender to the right of the bridge center connects to the main cable. We will be taking all the points between G and M into consideration. F1 through F7 are the suspender reactions supporting the crossbeams. T0 is the tension to the left of point G, and T7 is the tension to the right of point M. The angle at which T7 is projected is unknown, therefore we will be dealing with the components. Now using the equations of equilibrium, we find that T7y is 7 meganewtons and T7x to be around 25 meganewtons, which gives us T7 to be 25.96 meganewtons. Using the components, the angle can be determined to be 0.273 radians. What is the total rise in the main cable from its lowest to its highest point? The total rise is calculated to be 8.7 meters. Lastly, consider two different main twin scenarios, an approach symmetric to the main span and an approach cable at 45 degrees. The first scenario, we got both tension forces on either side to be at the same angle we calculated previously. Let's look at their components and solve for Fy of the tower, which is found to be 14 meganewtons upward. For the second scenario, one of the angles is the same but the other is at 45 degrees. Taking the components into consideration, we'll solve for both T8 and Fy, which are found to be 35.4 meganewtons and 32.04 meganewtons respectively. If structural steel can carry 260 megapascals, that is 260 meganewtons per meter of cross-sectional area, what cross-sectional area A must the cable have? Taking the scenario with a 45-degree angle, the area is found to be 0.136 meters squared. What diameter must it have? Using the area equation, we find that the diameter is 0.42 meters.